Hello, everyone. My name is Alabi Adebusola. She got the pronunciation anyway. So I'm going to be talking about galaxies that look like this, ultra diffuse galaxies. I know you've seen this image twice today. Yeah, so I'm going to skip the introduction, but then I'm going to be talking about how we think ultra diffuse galaxies in cluster environment, in dense environment, in particular Coma cluster, how they formed. So the results I'm going to share with you, we recently published them in a two-paper series, and I've got the papers up on the screen and implore you to check them. So essentially what we've done is that we've looked at ultra-diffuse galaxies in velocity phase space, and then we've also done some stellar population analysis, just to know if these galaxies, if they are recent infalls into the cluster environment, and then to understand how they form their stars, how long they form their stars, when did they stop forming their stars, is there any link between the infall time, assuming they're actually recent infalls, and when they stopped forming their stars. So these are the results I'm going to share with you shortly. So one of the things we've done is that we've gone to the Coma cluster because it's very rich in ultra-diffuse galaxies. So essentially, we've used the Coma cluster as a laboratory to efficiently understand how ultra-diffuse galaxies form. And it's no surprise because the ultra-diffuse galaxy discovery paper already shows us that there could be up to 48 of these galaxies in the Coma cluster. And then from Yagi's low surface brightness galaxy catalog, we know that there could be up to 300 candidate ultra-diffuse galaxies in the cluster. So we've got lots of targets that we could pick and then follow up on. But the interesting thing is that despite the abundance of ultra-diffuse galaxies in the Coma cluster, very few of them has been spectroscopically confirmed. And this is obviously because they're very faint, but that's not the only reason. Their spatial extent on the sky is also huge, and this is a factor when you want to do spectroscopy. So essentially what we've done is that we've used multi-object spectroscopy to study ultra-diffuse galaxies in the Coma cluster using beamers on cake. And here on the screen, I'm showing our targets as green squares in the size luminosity plane. So we picked 25 galaxies from the Yagi catalog, low surface brightness catalogs, and you can see from the plot that only 3 of them fall below the size criterion defined in the Peter van Doeken's discovery paper. So we've got 22 ultra-diffuse galaxies in a sample. The other thing I would like to point out is that just to get enough light from each of our targets, we used slits that are 3 arcseconds wide. So at the distance of Coma cluster, this corresponds to 1.5 kiloparsec, and that really helped with the study. And because of these, we ended up with a spectral resolution of 14 angstrom. Now, 6 of the galaxies in our sample also belong to the original Dragonfly catalog. And just to optimize the use of the real estate on our mask, we added filler objects anywhere we had gaps, on the mask. It's going to be important as we move on later in the talk that we should note that our sample is not complete in any way. It's neither complete as azimutally because obviously Coma is very big and we can only do as much as we've done. And then you can see from the plot, the pink part of the plot, that we've preferentially picked things that have higher surface brightness, but then they are still ultra-diffuse galaxies based on the definition. So this is what our galaxies look like. Each of the thumbnail I'm showing here is 10 kiloparsec by 10 kiloparsec. And then we used 2 masks, one within the projected, one within the core of the cluster. It's at a distance of 0.5 megaparsec from the cluster center. And we integrated on that mask for 14.5 hours. Then the second mask is in the outskirts, and we only stayed on it for 2 hours. And if you're familiar with Coma cluster, you can see our mask with respect to the 3 most luminous galaxies in the cluster. So straight to our result. So what we've done here is that we've now assembled the largest, up to now anyway, the largest spectroscopically confirmed catalog of ultra-diffuse galaxies in the Coma cluster. Out of the 25 targets we looked at, we were able to show that 16 of them are actually UDGs consistent with being Coma cluster members. And that brings the total number of UDGs in Coma cluster to, spectroscopically confirmed, I should say, in Coma cluster to 25. So what I'm showing on the screen here now is our velocities against their distance from the center of the cluster. And our measurements are the blue circles with the black edges. And you can see that within the cluster core, 0.5 megaparsec from the center of the cluster, we have a lot of measurements. And then in the outskirts, we also have 5 new measurements. So I'm also showing literature values. Up until our study, there were only 9 Coma cluster UDGs that have been spectroscopically studied. From our study, we also measured one UDG from the catalog that is consistent with being a cluster background object. And that's what I'm showing here as Yagi 771. So that brings the total number of objects that UDGs that are not within Coma cluster 2. And what it tells us is that the photometric catalog from which we picked our target has a very low contamination rate. Indeed, we estimated it and it's less than 5%. So you can be sure that if you pick anything from that sample, we're really picking an ultra-diffuse galaxy that is in the Coma cluster. Another thing I would like to point out from this plot, which by itself doesn't tell us anything about how UDGs in the Coma cluster formed, is that if you look within the cluster core, you'll see that the velocities of the UDGs we've detected, they're pretty much, they don't look so different from that of the background Coma cluster galaxies. But then as you move towards the outskirts, we start seeing an effect. It seems that the average velocity we've measured, and the same from the literature values, it's a bit elevated compared to the systemic velocity of the cluster. But then we suffer from a lot of incompleteness in this region. So take that as it may. So in this plot, I'm showing the UDGs from our study and also from the literature. I'm showing their optical colors on the y-axis and then showing the distance from the cluster center on the x-axis. But what I've done is that I've color-coded them by their relative absolute velocity. So what you will see is that within the cluster core, UDGs that are moving fast, they tend to have a bluer color. Now, it's important that you know that UDGs are essentially red, low surface brightness galaxies. So when I say bluer, it's in a relative sense. They're still red galaxies, but then they're just bluer than those that are moving with slower velocities. And this is very important. As we move on, you'll see the reason why I think it's very important. But then, in understanding this plot, you have to bear in mind projection effect. Some of the UDGs that are within the cluster core could actually be further out into the cluster. So I'm showing another version of this plot now, but what I'm showing here now is the relative velocity on the y-axis against the sizes of our UDGs. But then I'm focusing on the UDGs within the cluster core. And I've actually color-coded them by their actual optical colors. And you will see that there's a trend now that fast-moving UDGs, which I showed in the earlier plot, to be bluer, they now have smaller sizes. And this is not the first time something like this has been done. Now, Liska in 2009 showed that there's a correlation between the structural properties of some Virgo cluster dwarfs and their velocities. So what we are saying is that fast-moving UDGs, at least within the cluster core, they are bluer and they are smaller. Now, in the next plot, I'm going to combine the position of UDGs within the cluster environment, their relative velocity, and their optical colors in a modified phase plot, just to show you what we think is really happening with the origins of UDGs. So like I said, I'm showing on the y-axis the optical colors of our UDGs. And on the x-axis, I'm showing a proxy for the info time. So just think of it this way, that as the cluster increases its mass, infalling galaxies are going to have higher velocities. So at earlier times, infalling galaxies at smaller velocities, and you're going to find them at the upper left corner of the plot. But at later times, when the cluster had gotten bigger and the gravitational potential had deepened, the velocity of infalling galaxies will be higher, and then you preferentially find them in the outskirts. But then there's confusion from projection. But then if you compare this plot with the slide I showed just 2 slides backwards, you'll see that it's like things have moved from the center to the outskirts. So here we have less confusion from projection effect. So to properly understand what is happening again, I've shown the three most luminous galaxies in the Coma cluster just to quantitatively understand the info proxy we show on the x-axis. And in agreement with literature results, you see that NGC 4839, which is obviously a recent infall into the cluster environment, based on our new analysis, is also a late infall. And another thing you're going to find, you'll see from the plot, is that our recent infalls appear to be bluer. So what we think is happening is that bluer UDGs from our sample in the Coma cluster, they are consistent with being late infalls into the cluster environment. But I don't think that's the most important thing from this plot. What it shows us is that obviously not all UDGs within the Coma cluster environment are recent infalls. So we think this means that the origins of UDGs within the Coma cluster environment is diverse. And that's important as we begin to understand how UDGs are formed. So for comparison, I've also shown a sample of higher surface brightness dwarf galaxies from Smith 2009. And you can see that pretty much they follow the same trend. Now you might ask yourself that, we know a fraction of UDGs in the Coma cluster are recent infalls, while some of them are pretty much primordial galaxies. But then do we see the same evidence from their stellar population? So 7 of the UDGs from our central mass have high enough signal to noise ratio, and we can perform stellar population analysis on them. So again, I'm showing our central mass, and then the UDGs that have high enough signal to noise are shown as cyan. The filler objects that we're also able to do stellar population analysis on, they're shown as black and yellow. So prior to our study, like I said earlier, only 4 Coma cluster UDGs had their stellar population characterized, and I'm showing them here. So this work has added 7 to the list. And the summary is that UDGs essentially have the luminosity weighted age of stars in UDGs, span from 4 to 9 gigayears, and then they are metal poor stellar systems, and the alpha abundance is slightly supersolar. And this is in agreement with all the other UDGs that have been studied in the literature. But then to properly understand what is happening, we're going to convert the star formation history of our UDGs into cumulative stellar mass, and then we're going to plot it against look-back time. So I'm going to just ask that you focus on the cyan lines and then the purple lines. The purple line is for massive early-type galaxies from the Coma cluster, while the cyan line is the average for our UDGs. Around 50%, you'll see that UDGs and the early-type, massive early-type galaxies, they form 50% of their stellar mass at different times. Early-type galaxies just get on with their business early on. Within 2 gigayears, they've already assembled 50% of their stellar mass. Unlike UDGs, it takes them 7 gigayears to do that. But then, if you look again at the plot at the 90% level, which is a fair approximation for the time galaxies stop forming their stars, you'll see that UDGs, it takes them 11 gigayears to stop forming stars. So for some weird reason, UDGs can sustain star formation for 11 gigayears, unlike other galaxies within the cluster environment. And we think this agrees with our previous result, where we show that the bulk of our UDGs for this sample, and it's very important that we bear in mind that this is an incomplete sample and it's unique to the Coma cluster. You could find different results in different environments. But the bulk of the UDGs we have studied in this work, they are consistent with being quenched 2 to 3 gigayears ago. And this is the summary of our results from the 2 papers, which I think it's very, very, very important that we bear in mind. There is a diverse origin for UDGs within the Coma cluster. Some of them are recent infalls, while a few of them have been in the cluster environment for as long as we can think of. And then the star formation history of UDGs is extended. We find evidence that UDGs have sustained star formation for the past 11 gigayears. Thank you.
How these different properties or the 2 formation
Yeah, it's one of the things we're thinking of doing. So there's a recent paper by Lim and Peng with HS Digital. Unfortunately, we only have 3 UDGs in common. We only have 3 UDGs in common. But if I could go back to this slide, I can show you that all the UDGs with high specific frequency, you would find them up here. So yeah, but then with just 3 of them anyway. Yeah, so that's a caveat you should bear in mind. We'll hopefully maybe in the future would have better overlap between the 2, and then we'll be able to do a better matching. But for now, that's just the way it is. Yeah.
So I wanted to understand why you think it's diverse origin, because naively it looked to me like if you've got these things that are falling in now that are already ultra diffuse, doesn't that suggest it's not environmental, or is I guess I was thinking in my head there's environmental origin and there's some kind of like puffing myself out origin.
Yeah.
If they're falling in already puffy, doesn't that say that that's probably it, or is there something else going on?
Yeah, I get what you're saying. So, but the idea here is that the things that we see that are consistent with being early infall, we don't really have any evidence that they are early infalls. It's possible that they formed when the cluster started forming, that they've been in the cluster for as long as even the most luminous galaxies there. They are consistent with being early infalls, but then they could also be primordial galaxies. They've just been there for forever.